go, Dave. Hi, good morning. Welcome to our science seminar today. Hopefully you guys, left all your guns in your cars before you came in to school today. Right? Because that's what we're talking about. Firearms and all kinds of stuff. Always brings in a big crowd of people. So Stacey is coming to us from down the road there at Tyler Regional Crime Lab. She has a degree, I think, in animal zoology or something like that.
Yeah, I have a Bachelor of Science in Animal Science. Yeah.
Okay, so she knows all about you guys. And she also...
I didn't say that. He said that.
She also has gone to the, what is it called, the National Firearm Academy?
Yeah, I'll get into that.
Yeah, she'll talk more about that. So she knows all about guns and crime, and she's going to tell you all kinds of fun stuff about what they do over there at the Tyler Crime Lab. So let's give her a warm welcome here.
Okay, my name's Stacey Phetteplace. As he said, I'm from the Tyler Regional Crime Lab. I work for DPS. It's one of the state crime labs. There's 13 throughout the nation. Can y'all hear me okay? I'm not used to talking to such a large group, so if you can't hear me, just wave or something. I'm really good at projecting my voice. So, there we go. We'll use the keyboard. I am a forensic scientist assigned to the firearms section. I am also known as a firearms examiner. We frequently try to say we are not firearms experts. We're more tool mark experts. A firearm expert knows all about ballistics and which bullets and which cartridges to use for whatever application. I really don't care. What I study is how the gun works and what kind of tool marks are left on the ammunition components. So we're not really firearms experts so much as firearms examiners. I've worked for DPS for about 11 years. The first 3 I was a technician. What I did was test fire guns and enter them into the national database and compare them to other offenses to see if they'd been used elsewhere. Then I became a forensic scientist, which involved going to the National Firearms Examiner Academy that was hosted by the ATF. It's in Ammendale, Maryland, at one of the national laboratories. The ATF, that program lasts about a year, and then I had an additional year of training with DPS, and they always have continuing training to stay current. I'm a regular member of the Association of Firearm and Tool Mark Examiners. I'm also certified by AFTI in the area of firearms evidence examinations. I've court qualified in several counties, in several courts, and I've toured over 23 firearm factories and ammunition factories. So what I'm going to talk to you today about is tool marks and how they're unique. I'm going to define the tool marks and talk a little bit about basic metallurgy. Are there any metallurgists here? Okay, I know nothing about metallurgy. I really don't. What I'm going to show you is something I learned a little bit in the spring, and it is the basis of our science of individuality for tool marks. So if I say something wrong, feel free to correct me because I'm always learning more about it. Then I'm going to show you the basic barrel manufacturing process of how most firearm companies will make a barrel. And I'll talk about the areas of interest for a firearms examiner when we examine ammunition components and the type of conclusions we'll come up with or arrive at after we've spent some time examining the evidence. So what are tool marks? To define a tool mark, we have to first define what a tool is. A tool is an object used to gain a mechanical advantage over a softer object. This often results in the softer object being marked by the harder object or the tool. The tool marks are defined as contour variations on the surface of an object that resulted from a combination of force and motion being applied by a tool either parallel to the object or perpendicular to the object. When a tool is applied parallel to the object, it results in striated tool marks. The striations are basically lines like what you see right here. They move across the surface of the object being marked. An impressed tool mark is applied, the force and pressure applied perpendicular to that object, so they're pressed down into that object, much like you see this head stamp where this all of this, it says 45 Auto Winchester, those are impressed tool marks. So here's the basic metallurgy. Metal is crystalline, which is a crystal within a crystal. The crystals are made up of atoms. When the atoms come together, they form different shapes. They can be very specific shapes, such as the face center cube, the body center cube, or the hexagonal closed pack. The grain boundaries that result when these atoms come together are where the metal gains its strength. The types of boundaries, there's numerous boundaries. There's probably more listed than what I have listed here. Interstitial, vacancy, substitutional, twinning, dislocation. It's just how they define how those boundaries appear and come together. When the metal is deformed, it increases in the strength by closing those boundaries together even more. So to deform the metal, or what we call deformation, resulting from forging or annealing or that type of thing, will cause those boundaries to close down and become stronger. So when the grain boundaries fracture, they'll fracture in a random pattern. Why? Because the atoms came together in a random pattern and the grain boundaries are formed in a random pattern. So when they finally come apart, it's again in a totally random fashion. Is everybody with me on that? You're nodding your head, so I'm still on the right page, right? This is from an old textbook. The top corner shows atoms that are starting to come together, and then this is where they're coming together and they're starting to form these grain boundaries that you see here, right in here. And so this line here would represent this grain boundary here, and you see that it's random and it's irregular in shape, and all these will lead to an irregular fracture when they come apart. This is a 1040 stainless steel. This is just an example from another textbook. Normalizing steel involves heating the steel up to a certain temperature and then just letting it air cool on its own at a regular rate. In annealing, the metal is heated up to a certain temperature and then it's allowed to cool at a defined rate. They allow it to cool to a certain temperature and they hold it at that temperature and then they allow it to cool the rest of the way. In oil quenching, you'll see it's also a way to cool it, but it's cooled more rapidly, and by dipping it into oil, it's still a controlled rate of cooling, but it's cooled faster than air cooling. And tempering is just another way of helping it cool at a staggered rate. You can see with this stainless steel, when it's normalized, when it goes through a normalizing pattern, these grain boundaries are really big, and there's lots of spaces in them, and it's not as strong as it could be. When it's annealed, I know it's a really light picture, but those boundaries are starting to close down, and through oil quenching, you see there's a lot more of these grain boundaries, and the atoms and the crystals are not that you can't see the atoms, but the crystals are a lot smaller, and so there's more grain boundaries, and they're closer together, so it results in a much stronger steel. Okay, before I get into the rest of this presentation, I'm going to go through some of our general terms. As I was building this yesterday, I was using terms, and I thought, well, I don't know what your firearms background is, so I better define some of these terms so that you know later on what I'm talking about. Class characteristics are intended manufacturing characteristics. So when a firearms manufacturer wants to make a barrel, they decide this barrel is going to have a 6-right rifling. Much like if Chevrolet makes a steering wheel, they want it a certain size and a certain dimension. And Ford's going to be, they have specifics as to how they want theirs to look too. So these are just general class characteristics that would indicate a particular brand or a particular model. They don't indicate a particular item. And individual characteristics are characteristics that are unintentional they're basically incidental to manufacturing. Individual characteristics occur during manufacturing, but they weren't intended by the manufacturer. It just is a side effect. if you will. Or it results from using that tool over time. So when you have a car that comes off the manufacturing line, it looks just like the car that was behind it, except when you take that car down the street and you get in a wreck, now it doesn't look like the car that was right behind it in the manufacturing line. And the same thing with a gun. When you shoot a gun, you start running bullets through that bore, those tool marks are going to change, and the more you use that gun, the more those tool marks are going to change and become unique to that particular item. However, during the manufacturing process, as I'm going to show you later, the tools that are used to make that also impart individual characteristics. So it's possible to take a consecutively manufactured, say 10 of them, and determine which bullets were fired from which one of those 10 barrels. I've done that study 2 or 3 times from different manufacturers, so I know it's possible. I've seen it. We call those validation studies. This is a cartridge. A cartridge consists of 4 components: the cartridge case, the bullet, the primer, and the powder. We're concerned with everything except the powder. And a lot of times you'll hear in the movies and the lay people will say, they won't call it a case, they'll call it a casing. A casing is a soft, flexible membrane used to encase meat, also known as sausage. A cartridge case is a hard case. And actually, one of the videos I show you, he also says casing, which is incorrect. But at least you know what we're talking about. With the cartridge, we have tool marks that appear on the bullet, the cartridge case, and the primer. Basic firearm parts, what we're focused on is the slide and the barrel. The frame, magazine, and recoil guide rod, they're just there to show you the relationship with the slide and the barrel. The barrel on a pistol also contains the chamber, and the chamber right here is where it holds the cartridge. The inside of the barrel is known as the bore, and that's where rifling marks, or where the rifling is, and that's where we get a lot of our tool marks on a bullet. This is the slide. From this angle, you see here's my little pointer's going out. The extractor is this little piece right here. What the extractor does when the cartridge is discharged and the slide starts to move backwards, the extractor grabs that cartridge case and pulls it out of the chamber. At the point that it reaches all the way back, it hits this ejector right here, and that ejector kicks that cartridge case out. So both of those items will also mark a cartridge case. Inside that slide, see, here's the extractor right here, and right here's the ejector. Now we have the breech face and the firing pin. The breech face I'll talk about quite a bit later, and it's actually what I thought when I started talking about breech face. I thought, well, there might be a lot of you that don't know what a breech face is. That's what the breech face is. And if you look closely, you might see some of the striated tool marks that are on that breech face that get impressed into the primer. This video I'm going to show you is on YouTube, and you know sometimes they come up with ads, and I'm going to try to get through the ad. This morning when I ran it, it was all in Spanish, so bear with me. This is just going to show you an animated view of a pistol being discharged. Yeah, it's not going to let me skip the ad, sorry.
Keeping electricity affordable. That's the power of your co-op membership. Learn more at togetherwesave.com.
I created this animation in order to explain how firearms function in a very basic, clear way, which requires no previous knowledge. The firearm used as the model, a 1911 semi-auto handgun, will be displayed with only some essential internal parts for the sake of simplicity and clarity. This is an individual unit of ammunition, the cartridge. It is loaded into the magazine, which contains a follower and a spring that keep the cartridges under tension. The magazine is designed so that the cartridges can only be pushed out forwards. The spring cannot push them straight out of the magazine. When pulling the slide back, it cocks the hammer. Upon releasing it, the recoil spring snaps the slide back forwards, which on its way grabs the cartridge and pushes it into the chamber of the barrel. When the trigger is pulled, the hammer drops and strikes the firing pin, pushing it forward. The cartridge consists of a casing which contains the bullet, the powder, and the primer. When the primer is hit by the firing pin, a chemical reaction inside causes a small explosion which ignites the powder. The powder burns rapidly, which increases the pressure within the enclosed cartridge dramatically. The resulting force propels the bullet, while equal force also goes in the opposite direction, pushing the slide back, which ejects the spent casing and cycles the next cartridge.
So that's essentially the cycled fire of a pistol. Get out of here. These 5 steps are the basic 5 steps of any barrel manufacturing company. This is what they go through. How they go about it can be proprietary in a lot of ways. But after I go through these, I'm going to show you a video that Ruger put out. And you'll see that anything that's proprietary from Ruger, they've hidden from the video. The barrel is cut from round steel stock. So they'll have steel stock that'll be up to 24 feet long. And they'll cut it down to the length that they want, whether it's for a rifle or shotgun or all the way down to the size for a pistol. When the next step is called gun drilling. So they take a drill bit and they drill a hole through that, and that deep hole drill bit it'll vibrate and chatter as it goes down, cutting through this hole. So it may not be a perfectly straight hole. So the next step is called reaming. They'll take a reamer and they'll go back down that hole, and that reamer smooths out that hole and makes it perfectly even all the way through the center of that steel stock. I've underlined reamer because the reamer gives us a lot of tool marks that we'll use later. When it spins around, it leaves marks that are perpendicular to the center of the axis of that hole. Those marks will show up later. Then after the barrel is reamed, they do the rifling. The rifling puts the number of grooves in it and puts the proper rate of twist in it. Does anybody know why they put rifling in a gun? It makes it shoot more accurately. That's right. Just like a quarterback throwing a football, you put more of a spiral on it, and you can more accurately hit the receiver. This is how they do this is through, they either cut it, they use a broach method or a button method or a mandrel. When they use a mandrel, it's called hammer forging, and they force the steel down over that bit. And the rest of these methods, they just pull that cutter or button or mandrel broach through, and it cuts the steel. So after the rifling is done, then they use the chamber reamer and they ream out the chamber. I'm going to show you this video next, and hopefully it'll work the way we want it to.
Ruger's barrel-making technology has been advanced greatly over the years. By implementing new technology and devising new techniques, we've provided some of the best-made barrels in the world. It all starts in the steel mill, where chemical composition and mechanical properties are meticulously controlled while making 20-foot long bars of steel round stock. The bars are cut to length and deep hole drilled 4 at a time, with a narrow bit slightly larger than the caliber planned for the barrel. Each drill hole is placed exactly in the center of the bar every time. The metal chips are forced out using high-pressure oil and are recovered in a reclamation machine, so they may be recycled. Following the drilling, the rod is placed in a series of CNC machines to be turned down to the correct outside shape and size, and both ends are trimmed. 100% gauged before being washed, debris blown out, and wiped down, this rod is now ready for the big guns, the hammer forger. The fully automated hammer forging machine perfectly forms the rifling in the interior of the barrel by literally pounding the barrel on all sides, squeezing it down around the carbide mandrel that is ground to the inverse of the rifling pattern. In the process of cold working the barrel around the mandrel, the barrel ends up a longer length, a smaller diameter, and at a higher hardness, with perfect rifling formed at precisely the right size and with a super smooth finish. It used to be at Sturm Ruger that all these operations were done independently of one another. Now, because of lean manufacturing improvements, we have placed all the steps necessary to forge a barrel in one cell to improve efficiency and quality. Robotically rolled down the ramp and then trimmed, this barrel is ready for machining at the Ruger plant.
Did you notice he said when they do their gun drill, their deep hole drill, that they actually cut it to a larger diameter than the caliber? Do you know why they do that?
Compress it down.
Right, exactly. When it goes in their particular manufacturing process, after they do that deep hole drill and they go to do the rifling, they compress that metal back down around that bit. So it has to be larger in order to fit the bit through it, and then it's compressed back down around it. Very good, thank you. This is a deep hole drill, or drill bit. The end of this bit, the cutting edge is right here, on this edge right here. It has a hole in it, and the reason for that hole is they push oil out through this hole, and as the bit turns, it cuts that metal, and those metal chips, they have to go somewhere. So the oil comes out this hole, and then it forces the chips back down this channel right here and forces them back out the hole. The oil also helps keep the metal from becoming overheated and changing the characteristics of the grain boundaries so that it stays a real strong steel. This top one is a bore reamer. This is what's used to make the final diameter of that rifle barrel. These little notches here they cut away some of that steel as well, and so they'll leave marks on the inside of that barrel that are perpendicular to the center of the axis. And then the chamber reamer, this end goes down into the rifling so it doesn't affect the rifling at all, and then this is cut to the exact cartridge dimensions that the barrel will end up shooting, or cartridge, where the cartridge will sit. This is a plastic model, and what I wanted to show you was these marks right here. This is from the reamer as it spins around. Now, this would be before the grooves are cut. This model actually has the grooves already cut into it, but I wanted you to see these little marks. What's interesting is because these marks go crossways, when the bullet travels over them, they'll change and get worn down. I'll explain a little bit more of that later. These are 3 different rifling tools. This is called a button. The button is, all 3 of these are actually pulled through the hole. They're never pushed. So this button has I don't know if you see that little line right here. You see how it leans off to the left? That's because it's from Colt Manufacturing. They put 6 left on a lot of their barrels, but the left-hand twist comes from that right there. The broach is similar. This one happens to be 5 right, and it came from Smith & Wesson. But with the broach, each one of these cutting edges is slightly offset from the last one. So you see how it leans off to the right? That's what imparts a right-hand twist on the barrel. This mandrel is, this one's actually polygonal, but it's very similar to what they showed you in the Ruger video, where you don't really see a whole lot of the actual rifling on that mandrel because it's so smooth. And so when the hammers pound that steel down around that mandrel as it's being pulled through, instead of actually cutting it. So when the barrel is hammer forged, it ends up being a lot stronger, which is why Glock's barrels, they're hammer forged, and some of Ruger's barrels are hammer forged, so they tend to be a lot stronger, and they're less likely to fail or bend or have a bulge in them. What I want to show you here is the board that's on the left. I'm sorry, would be your left, my right. This is what we call cut rifling. You can see this is really sharp edges and a very defined. This portion right here is called the land, and this portion right here is called the groove. So there's, I think on this one there's 6, or I never counted them. But this land is the part that has not been touched since it was reamed. The groove is what's cut by the button or the broach. On this bore, this is what we call polygonal. This bore was hammer forged, and you see how these edges are rounded instead of squared off like this. So there's a lot less of this bore that comes in contact with the bullet, so there's fewer tool marks on a bullet that comes down this bore. It results in a faster bullet because there's less friction. But you can see how that's all rounded, and that's what a mandrel does. When something's hammer forged on a mandrel, it doesn't fill in the little crevices, so it stays rounded like that. So now this is back to the model that I just showed you. This has the lands and the grooves in it. These are the grooves that were cut by the rifling tool, and then the lands. And you see the real tool marks are right here on these lands. What happens in the groove is as that button or broach is being pulled through, those tool marks actually are parallel to the axis of the bore, so there's fewer marks that end up on the bullet as a result of that because there's less friction. When the bullet travels down through that bore, those little ridges get broken off. Those ridges are various heights and depths and widths, and so they'll fracture all completely in a random fashion, which results in unique tool marks on the bullet. The groove, because it has less contact with the groove, there's fewer tool marks on the groove, although sometimes we do see bullets that have a lot of tool marks on a groove, or from the groove. So this is a land impression on a bullet. You see these marks here. You see how this is just an impression of the land. See, if you look back at the land is the raised portion, so the land is going to cut deeper into the bullet as the bullet's going down the bore. So when we get to talking about fired ammunition components, there's several areas that we focus on with the bullet, the land impressions, and the groove impressions. A bullet may have 3 land impressions. It may have 20 land impressions. It just depends on what the manufacturer intended. Based on those class characteristics, we can determine at least a short list of who may have made the gun that fired the bullets. With the cartridge cases, there's a lot of areas. When you saw in the cycle fire, you saw there's a lot of things happening with that cartridge case. So you have the breech face impression, you have firing pin impression, you have firing pin aperture shear marks, you have ejector marks, ejection port marks, and extractor marks. So there's a lot more going on with that cartridge case that we examine, and as well as chamber. I forgot about chamber marks. So back to this land impression. You see these little lines right through here? All of that, those are tool marks. Those are striated tool marks. This groove impression has a few, very few, but the land impression is where we see a lot of the tool marks, and that's usually where we'll make our determination as to where the bullet was fired. On a cartridge case, I want to show you this is an ejector mark up here. The breech face impression is, there's some marks here, and then all of these, what we call crosshatch, because they're kind of overlapped in different directions. Those are all breech face marks. This is the firing pin impression, and within that firing pin impression, there's unique and irregular marks. This is the firing pin aperture shear marks right here, and the firing pin drag marks. What happens with firing pin aperture shear marks, they don't show up on every cartridge case we looked at, but on some guns, the hole that the firing pin comes out is called the firing pin aperture, and it's rough cut because they just punch a hole through it so the firing pin can travel up and down through that hole. So when the cartridge case is pulled out of the chamber, it hits against that breech face, and then when it hits that ejector, it'll drag across that breech face and result in actually striated marks from being moved alongside that aperture. So these marks are actually striated, resulting from force being applied parallel to the primer. The firing pin drag marks are also striated, and what happens when on a lot of short recoil firearms like the Glock or like a lot of your real common handgun pistols, the 1911, when that cartridge case comes out of the chamber and hits, and as it slides moving rearward, the firing pin itself hangs up a little bit, and when that cartridge case hits that ejector, it drags across that firing pin, resulting in a striated tool mark, which is unique to that particular gun. These are chamber marks. These are from the chamber reamer. And the other part of this is when that cartridge hits when it expands because the gases force that cartridge case against the chamber, you'll get these striated marks like this, but they look like chatter marks too. So sometimes they're not this well defined. They'll be really little and short, and that's from chatter and vibration. So sometimes you don't get an exact match on a identification because of movement. Extractor mark. This is not necessarily proof of firing so much as a proof of cycling, but on this shotgun shell it's proof of firing because there's so much pressure in that shotgun shell when it is discharged that there's a lot of movement and the marks are real deep. If this had just been cycled through the firearm, these marks would have been very small and very shallow. So after we've looked at all of our tool marks that we get in a case, if we're looking at bullets, there's several different types of conclusions or opinions that we can formulate from the tool mark patterns that we see. We can identify them, we can eliminate them, or we'll have what's called an inconclusive result. With an identification, we say all of these were definitely fired in one gun or this particular gun. With an elimination, is like saying this is 5 right and this gun is 6 left. So there's no way these ammunition components were fired in this particular gun because the class characteristics are different. The inconclusive is kind of our gray area. What happens when we get a bullet from a deceased person and all the tool marks have been mangled by forceps or striking bone or things like that? That bullet is so damaged sometimes that those tool marks are obliterated. And so the class characteristics indicate it could be this gun, but the individual characteristics, we can't definitively say it's that particular gun. So an inconclusive result, it means it may have been that gun or it might not have been that gun. It may have been a gun of a similar make and model. Another reason we might say it's inconclusive is on poorly made firearms that are poorly rifled. We may not have tool marks in that land impression. We may have the class characteristics, but the tool marks themselves are just not there because there wasn't proper engagement. Which means just because the marks aren't there doesn't mean it's not the gun, or it doesn't mean it is the gun. So I'm going to show you some of our ranges, kind of just walk you through some of this. I tried to pick some that would be pretty easy to see. On this bullet, there's these patterns, these striated lines. I don't know, some people can see the patterns and some people can't, but when we have this level of pattern agreement, from this bullet and this bullet, can y'all see that dividing line? That means both these bullets were fired from the same gun. That's the only conclusion we can come up with. Now imagine if we had that agreement on all 6 land impressions. It's just virtually impossible to have been fired from a different gun. This is a cartridge case identification based on these impressed marks all throughout the breech face. These marks are actually striation marks from when the breech face was cut with a broach, but they were impressed into the primer, so we call them impressed marks, when they were originally striated marks on the actual slide. I know I've talked a lot about firearms, but another part of our discipline is examining tools. Copper theft is a real big thing. People steal copper because it's very valuable. So a lot of times we'll get copper in that's been cut, and we'll get a suspect's tool, and we'll have to determine if that tool cut that wire. This is probably one of the best tool mark matches I've seen. All of these lines right here, I mean, it's almost a perfect match. With this case, they've brought in 4 different tools and 26 pieces of copper wire. So it took me a lot to go through and figure out which tool to focus on and then which tool marks I needed to look at. With a tool, well, let me back up. With a firearm, when a bullet goes down the bore, it goes down the bore the same way every single time. It doesn't matter who's pulling the trigger or if they're shooting left-handed or right-handed or up or down or however they want to shoot it. With a tool, now we have to consider, is he left-handed? Was he right-handed? What kind of force and torque did he put on it? Did he twist the tool as he was cutting it? All these can affect the tool mark because it affects what part of that tool came in contact with the wire. This is an inconclusive. What we have is the class characteristics are the same. This land impression is the same on both sides. There's this little engagement mark right here that's the same on both sides. But there's not sufficient tool marks in the middle of that to be able to say that it was from the same gun. So I can't say it's not, but I can't say it is either. This is an example of an elimination. This land impression goes from here to here. And on this bullet, it goes from here all the way down to here. So the width of that land impression is completely different. So there's no way one was fired, these 2 bullets were fired in the same gun. This is a cartridge case elimination. What probably jumps out first is these marks right here. These are breech face marks. Just because this doesn't have them doesn't mean it's eliminated. It just means they didn't reproduce on the primer. What does make these 2 different is this firing pin impression is circular and this firing pin impression is elliptical or almost egg-shaped. So because of that, there's 2 completely different firing pins struck these 2 primers. This is coming back to that same copper theft case I was talking to you about earlier. This piece here was cut by a shearing tool, and what a shearing tool does is like your scissors or tin snips. They have 2 blades that oppose each other, and one blade holds still and the other blade passes over it, which results in this lip on the top of that copper wire. So that's a class characteristic. When I see that, I'm like, this definitely was cut by a shearing tool. However, the one on this side, you see where it comes together in the center, that was cut by a pinching tool with a center cut, like wire cutters. So there's no way the same tool cut these because there's completely different class characteristics. So in conclusion, there are several elements that affect the tool mark and what makes it so unique. Random crystalline structures that come together randomly, they fracture apart in a random fashion, which adds to the uniqueness of each tool mark. The manufacturing process involves cutting and a lot of tool chatter or movement through that, so it results in more uniqueness. And also the tool use and abuse. If a tool like the wire cutter or the shears that were used to cut the wire, they had been used for so long they almost couldn't cut the wire. The head on it was probably this big, and I'm cutting wire this big, and really had to use some force to get through that wire because it was so worn out. So it had a lot more use on it, and probably poorly used. So it just shows that our opinions are also based. They're based on similarities that we see, but they're also based on what doesn't agree. So we consider the differences. The way we say it in the lab is we compare and we contrast. Because a lot of times you'll see things that, oh, here's a little area. Well, this is like 3 lines that match. But over here there's 20 that don't. And so we compare and contrast. It's not just comparing. A lot of times when we look at evidence, we may decide we're going to look at it as, when I look at it and think, okay, the officer thinks these two came from the same gun, but I'm going to prove him wrong. And I start going through and I find what doesn't match, and then eventually I get to the point of there's so much that does match that I decide that those two bullets came from one gun. And it's real tricky for our science to stay unbiased. And that's where this compare and contrast, we focus on the science instead of what we want it to be. Are there any questions? I went through this pretty quickly.
How much grief do you get from defense attorneys when you bring inconclusive results to trial?
I would say the defense attorneys love an inconclusive result. They don't. The prosecution is they don't like an inconclusive result because now that we've opened up that area of doubt for the jury. I had one case down in Jasper. I was really surprised I got called to testify on it, since they submitted 2 guns and it was a homicide, and I eliminated both guns from firing the bullets. And the prosecution asked me to come testify anyway. And it's funny, a lot of the lawyers, they don't really prepare for these cases until it's right in front of them and they're in front of the jury. And so when I said, and it said in my report the guns were eliminated, when the defense got a hold of he's sitting there reading the report and he says, "They're eliminated?" He said, "What does that mean?" And I said, "It means there's no way they fired these bullets." And he was so elated. It was like a kid at Christmas, and he went on for probably 25 minutes. "There's absolutely no way this happened." And I said, "No." So it's interesting. It's the reaction we get sometimes. What is your question? There's somebody over here.
Hi.
Ah.
Do tool marks change over thousands of firings in a firearm?
Yes, and that's a very good point. Because we have the wear, and you have that wear down, and so things can change over thousands of firings. From a forensic standpoint, most criminals aren't shooting their guns thousands of times, so we don't see a whole lot of change. But let's look at an officer-involved shoot. When we compare officer-involved shoot from this case to one a year from now, well, he may have run 5,000 rounds through that gun, and so there could be changes enough which will lead us go from an identification to an inconclusive because of that. And officers a lot of times will clean their guns with steel brushes, which also tear up the tool marks. Yeah. Good question. Okay. Two of you.
When a bullet impacts, the copper casing or the copper jacket will often kind of fragment. Do you have anything to do with how that's actually gathered and everything to be read properly?
As far as the fragments? I don't understand.
The outer copper is likely what would be marked by the grooves and everything.
Right.
So how is that gathered to be analyzed?
I don't work crime scenes, so I don't know how they collect their evidence. Okay. But we do get fractures. A lot of time we get fragments, bullet fragments. They'll still have tool marks on them. And I've taken a fragment and taken 2 fragments and been able to line up the tool marks on both, on the land impression that's on both, and be able to say that those fragments were once part of one bullet. They can maintain themselves. The smallest fragment I've identified is 1.8 grains. So pretty small. Yeah. Yes?
You said you have been to over 23 factories or so. Is that merely for educational purposes, or do you also enforce firing regulations and manufacturing processes?
That's a good question. ATF enforces all of the rules and regulations. So most of all my tours have been on an educational standpoint, and it's interesting because when we're in training, we have time and the resources to do these tours. But unfortunately, the tours a lot of times are wasted on the naive. So we go and we don't know what it is we're looking at, and the more you go, you say, yeah, I've seen this before, but in another aspect you haven't. And so now that I'm fully trained, I wish I could go back through all those factories, because now I know what to look for and I know what questions to ask. Yes, sir.
What would happen if one of the projectiles came from a smoothbore weapon? Like, not a shotgun, but like a smoothbore. Yeah.
Okay, I had a Derringer once that they forgot to rifle one of the, it was a two-barrel Derringer, and they forgot to rifle one of the barrels. So it was smooth on top and rifled on the bottom. With a smoothbore, a lot of times there's not any tool marks. With this one, there just wasn't any rifling marks. They still had tool marks. I've not seen it. One of my fellow examiners had a shotgun with the pellets, but the shotgun was cut off on the end. And so when the pellet passed, was that it? Yeah, the tool marks that had resulted from them cutting that marked on those pellets, and they were actually able to do an identification. That's some serious patience. Yes, sir.
Have you worked at all with either 3D printed or plastic or other non-conventional types?
No, it's still in a research phase. Well, the universities, I know Sam Houston University has got one, and some of our colleagues in Garland and Houston are working with them to do a research paper on that. So I really don't know a whole lot about. I've seen the videos, and they've made guns that will fire, but I don't know what about the tool marks. But if you will bear with me, I'll tell you something that Smith & Wesson is doing, and it's called electromagnetic rifling. Instead of cutting the bore, they take a copper and plastic mandrel and they put it down that bore, and then they pour an electrical fluid through there, and they heat that electrical fluid up, and it melts the rifling into the bore. So you don't really have tool marks in the manufacturing process. But what happens before it leaves the factory? All guns are test fired. The bullet goes down the bore, now we got tool marks. So a lot of times we hear about things and go, oh, this is really going to make our job more difficult. But in the end, the bullet still goes down the bore and it's still going to create tool marks because it causes that friction, which causes the fractures. And good question. Anybody else? Yes.
Is there any way, can you tell us something about how y'all try to avoid bias while you're analyzing these things?
That's a very complex question, and I don't know that I have enough time to answer it. It can be tricky, and a lot of times when we're looking at evidence, I try not to learn anything I can about the case, and I don't encourage the officers to submit a case report, and if they do, I don't read it. I don't want to know anything about it, so all I want to know is, did this bullet come from this gun? I don't know who had the gun and all that. So that's a big step towards the bias reduction. However, another part that I've struggled with, and I don't know if I should say that, but you get two difficult bullets on the scope, and you're looking at them, and you spend days and days looking at them, and I know they were fired from the same gun. The best thing I can do at that point is put it away for a week and come back with a fresh mind on it. And then I go, oh, okay, this is an inconclusive. The other thing is when you start looking at patterns over and over and over, by the end of the day, your mind starts seeing a pattern that isn't there. And it gets frustrating. So, and my supervisor's right here, so he understands why by 3 o'clock the examiners are walking around talking to people and they're not doing their job. Well, in a way they are, because that's how we control bias when we're looking at two different objects on the scope. And then we come back the next, and I may see something and I'll put a little, you saw some of those pictures where there's a colored marker dot on them. It's what we call an index mark. And I may put a little index mark on there, and then I'll put it away, and I'll come back the next morning with a fresh mind, and I'll look at it and go, what was I looking at? And I'll take the index marks off. So yeah, that's a good question. And actually there's seminars that'll go for 2 hours about bias and how to control your bias and conformational bias and things like that. Yes?
Do you have multiple examiners look at samples to make sure that you're being accurate, or do you usually do it sort of on your own? Like one examiner does one sample.
Okay, that's a good question. A little bit of both, really. I go through a case, and if I'm having trouble with one, I'll go get one of the other examiners and say, hey, what do you think of this? If I'm not having any trouble, it doesn't really matter, because in our lab, we have 100% verification. It doesn't matter what our opinion is, another examiner will go back through that case and verify that we have the right opinion. So when we have a report goes out, it's correct because 2 examiners arrived at the same opinion. And that's another way we reduce bias.
You ever had a case where one examiner said yes, the other one said no, the next one said yes, the other one said no, and it became a big controversy of we don't really care.
I'm trying to think if I had that. I've never had it go through 3 examiners. So typically, if I have a case and it goes to verification, when my verifier looks at it and he goes, you know, I really don't see what you're seeing. I really can't agree with your opinion. We'll go back and discuss it, and either I'll show him what I saw, because maybe on my scope I can get the lighting just right and he can see it, or maybe I'll put it on my scope and go, ooh, you're right. We're getting back to the same thing where I made an opinion when I probably should have waited till the next day to make that decision. And then I can change my opinion before the report goes out. It's very rare for 2 examiners to be absolute. This is absolutely an identification, and the second examiner goes, there's absolutely no way. Usually we work it out that way, but if there's a complete opposite opinions like that, then it goes to a 3rd examiner for more verification. And then whichever way he usually decides is usually how it ends up. And I can tell you the very few times that has happened in our system, inconclusive is always the right answer.
Okay, if you have more questions for our speaker, I'm sure she'll be around here, and she can join us for lunch in the Joyce Room. And let's thank her again. See you all next week.
That went well.